Hello everyone, my name is Brian Schmidt, and today I'm going to tell you about the accelerating universe. Now, the accelerating universe is not a story that is just my own. It really is a story about cosmology and the 100 years of development over the past century. And so let's first start with a tour of the universe. And the first thing I want to say is that the universe is big. Now, to understand just how big, we're going to use the speed of light as our tour guide, and the fact that it travels 300,000 kilometers per second. That's 7.5 times around the Earth each second. So, for example, when Neil Armstrong took his one small step, well, we found out about it 1.5 seconds after that event occurred. And the radio waves from his voice were transported right down the road here at Honeysuckle Creek and then transported around the world. You may not realize it, but the sun is 5 light seconds across, so much bigger than the Earth-Moon system. The reason the sun is so small in the sky is because it's so far away, about 8 light minutes in distance. Now, our sun is only one of many stars in the sky. The nearest of stellar systems is Alpha Centauri, the brighter of the two pointer stars to the Southern Cross. Alpha Centauri is a star not dissimilar to our own sun. And I want you to imagine it being a pea. If it were a pea and sitting here in my hand, and we think of the sun being another pea, where would the sun have to be the right scale? Well, about Sydney, 270 kilometers away. Everything in between is empty space. And so you can see why we call space space. There's a lot of it out there. So if we look out to our own galaxy, we see our sun is some 30,000 light years from the center. And our sun is made up of not just 1 or 2 stars, but 100 billion stars like our sun. And so it's a very exciting part of the universe, but only a small part of it. Looking further afield, we can see the nearest galaxies. The large and small Magellanic Clouds, right down here, are little satellite galaxies of the Milky Way. They contain 10 billion and 1 billion stars respectively, but they're tiny little galaxies that don't amount to much. The first real galaxy of any size is the Andromeda Spiral, about 2 million light years in distance. It's a galaxy that's a little bigger than our own Milky Way, but just the tip of the iceberg. Here we are looking only in the nearest part of our own universe. The most distant image that we have been able to take of our universe thus far is with the Hubble Space Telescope. And this is the image we call the Ultra Deep Field. In this image, there are about 5,000 galaxies. Each of these galaxies is not dissimilar to our own Milky Way, containing hundreds of billions of stars. And so this part of the image, this part of the universe, very small, is 1/32 millionth of the entire sky. And so while the universe is huge, at least the part we can see is not infinite. We take 32 million pictures like this, and we've seen it all. And the reason we can see it all is because the universe, although very big and maybe infinite, is not infinitely old. If we look back 13.7 billion years ago, we see a picture of the sky that looks like this. This is an image taken in microwaves and shows not stars and galaxies, but little ripples of sound left over from the Big Bang. Each one of these ripples is a sound wave, which eventually forms tens of thousands of galaxies. And before that, of course, we have the time of the Big Bang. All right, so let's go to the beginnings of cosmology and figure out how we learned all of this. I really see the beginnings of cosmology when we were able to take the light from stars, spread them out into the colors of the rainbow, something we call a spectrum. And a spectrum of a star reveals what the star is made out of, because every element has a fingerprint of light and color, which it absorbs and emits. So, for example, sodium has a fingerprint where it emits an orangey yellow color, which you can see in, for example, lights around airports or in other places that have sodium lights. Neon has a similar fingerprint that gives you the fingerprint of a neon sign. Well, Vesto Melvin Slipher in 1916 took the light of not stars but galaxies, sped them out into the spectrum, and he saw that these galaxies looked a lot like stars, but with a difference. And that difference was that the light was stretched redward. And Slipher knew that what that meant from something we called the Doppler shift. So if you look at, for example, a police car that's coming towards you, its sound waves are compressed by its motion. And when you compress sound waves, you raise the pitch of sound. As that car goes past you, well, then you're seeing the sound waves which are stretched rather than compressed. And when you stretch sound waves, you make the sound lower pitch. Now, light is a wave, and so it is affected by the exact same process. And that process for light is when you compress light, so an object moving towards you, the light is made bluer. And when you stretch light, well, the light is made redder. And so when Slipher went through and saw that all these galaxies' light was stretched, he realized that all of the galaxies in the universe seemed to be moving away from us. There are a few nearby objects which are actually coming towards us, but very, very few, only a handful. And so this was a big mystery in 1916. Why would all the galaxies in the universe be moving away from us? It seemed to indicate that we were a special place in the universe, a seemingly very unpopular place in the universe, which everything else was trying to get away from. So trying to unravel this mystery took some time, and it took being able to measure distances. Now, measuring distances in astronomy is not easy. We cannot lay down a ruler between us and the nearest star or galaxy. Instead, we have to resort to how things appear. So, for example, a candle or any light source appears fainter the further away it is. On the other hand, a ruler, of course, appears smaller the further away it is. So, Edwin Hubble was able to use a law that Newton had come up with, that is, the inverse square law, which says that, for example, if you have a light bulb and you move it to half the distance, that appears 4 times brighter. And so by judging how bright objects are in the universe, one can judge how far away they are. So Edwin Hubble in 1929 looked at the stars in Slipher's galaxies, and he realized that the faster the galaxy was moving away, the fainter its stars were. Or in other words, the further the galaxy was, the faster it was moving away. And to show you his data, here is his data from 1929, and we have plotted here brighter stars, meaning nearby distances, fainter stars, meaning further distances, and then on this diagram, these are the bottom part of the diagram is slow-moving objects, fast-moving objects. And from this data, he said, wow, there's a relationship. The further away you are, the faster you're moving. And he said in 1929, this means that the universe is expanding. And to give you an idea why Hubble said that, let's make a little toy model of the universe. So here we have a universe full of galaxies, which, thanks to the power of a computer, I can expand. And when I expand those 2 images, and look what's happened, and I'm going to overlay them from a reference point in the center, you can see that nearby objects have moved a little bit. Distant objects, for example, have moved a lot, here, here, and here. And so you can see the further away you are in an expanding universe, the faster you move. Just what Hubble saw. And furthermore, it affects all the parts of the universe the same. So if I overlay those images at a new spot, I see exactly the same thing. We aren't a special place in the universe. Now, it's nice to think of this toy model, but you really want to understand things in the universe with a theory. And our theory comes from Albert Einstein, widely respected as one of the greatest physicists of all time. In 1907, Albert Einstein had a revelation that acceleration due to motion and acceleration due to gravity were indistinguishable. That is, imagine you are in a box and you are on Earth and you don't know where you're at, and you feel yourself being accelerated by 9.8 meters per second squared, the gravity of Earth. Albert Einstein's thought was that you cannot tell, using any physical test, whether or not you're on Earth or in a rocket ship that's speeding up at that acceleration rate of 9.8 meters per second squared. A very simple thought, but a thought that took him 8.5 years to reconcile with mathematics. The result? His field equations. And it predicted many things, including curved space, and it allowed him to do something for the first time, something that Newton was never able to do. That is, solve for cosmology, how the universe behaves on the largest scales. Now, he did this in 1917, and he got a nasty surprise. He found that the solutions for the universe were dynamic. That meant that the universe had to be in motion, had to be expanding or contracting. And in 1917, that was 12 years before Hubble made his great discovery. And so Einstein did what any good theorist does when they have a theory, which they're sure is right, but doesn't quite fit the observations. You come up with a fudge factor. And his fudge factor was the cosmological constant. This is sort of like energy that is part of the fabric of space itself. At least that's how we think of it now. Of course, it was realized later on in his life, when Hubble discovered the expanding universe, that the universe really is in motion, and that Einstein could have predicted it from the basis of his theories, along with everything else he predicted. But it also turns out mathematically the universe wouldn't sit still even with the addition of this stuff. So the idea of this stuff is you'd add some of it to counteract gravity, because this stuff causes gravity to push rather than pull. And we're going to come back to this later on. So under Einstein's view of the universe, things are a little different. When we look at distant objects, we're looking back into the past because light takes us time to reach us. But the light, as it travels to us as a wave, is traveling through expanding space. And so it's not so much that the objects are necessarily moving away from us. It's rather that they're traveling through expanding space. And the further the object is away, the more it has to travel through expanding space, so the more it is redshifted as it gets to us. So imagine a universe which is expanding. Let's put it in reverse. Things get closer and closer and closer until, voila, you get to the time of the Big Bang, the time when everything in the universe is on top of everything else. And so the Big Bang is sort of a natural consequence of an expanding universe, having a time when everything was on top of everything else, very, very dense. So to think of this graphically, imagine I have two galaxies separated by some distance at some time, and if I go through and I run the universe back with this line, and this line is the expansion rate of the universe, what we call Hubble's constant. So the steepness of this line tells you how old the universe is, and the steepness of this line is the value which we call the Hubble constant, the rate that the universe is expanding today. So by measuring how fast the universe is expanding, you can figure out how old the universe is. Now, I thought this was a great thing to know back when I started my PhD in 1989 at Harvard. And so 3 years, 11 months, and 4 days later, but who's counting, here I am showing my PhD supervisor, Professor Bob Kirshner at Harvard, my result for the expansion rate of the universe. And you can see I'm very excited about it, and because the answer that I got was that the universe is about 14 billion years old, or that's a Hubble constant of 70 in current measurements. Now, it turns out I was part of a larger discussion throughout the community that was figuring this number out. The eventual answer was decided using the Hubble Space Telescope, co-led by Professor Jeremy Mould, the director of Mount Stromlo Observatory, and the man who brought me here to Australia back in the end of 1994. So we think the universe is about 14 billion years old. But there's an extra complication. When I showed you this diagram, that line is straight. But what if gravity is slowing the universe down? We expect, by Einstein's equations and just common intuition, that gravity is going to pull on stuff. And so just like a ball that I throw up in the air and the Earth's gravity pulls and slows down, I expect all the gravity in the universe to pull on the universe and slow it down. And so this universe, you can see, is not as old as it might otherwise be. Indeed, if we went through and added a reasonable amount of gravity to the universe, instead of being 14 billion years old, might only be 9 or 10 billion years old. And that might be a problem because we're pretty sure the oldest stars in the universe are at least 12 billion years old. And we cosmologists aren't too fussy, but it is useful for the universe to be older than the stuff that's in it. Now, when we look at a diagram like this, we can also project into the future. So imagine I look at a universe which isn't slowing down. This is a universe which is empty and coasting. It just keeps on going at the same rate, gets bigger, bigger, and bigger, and bigger. This is a universe which goes on forever. It is infinite into the future. On the other hand, you can imagine a universe which is slowing down. Here's a universe, if it's slowing down quick enough, will reach a maximum size, halt, and then go into reverse, just like the ball that I throw up into the air. So while both these universes start with the Big Bang, this second universe, of course, ends differently. It ends with a Gnab-Gib. That's a Big Bang backwards. All right. So as a review, the slowing down of the universe affects how old we think the universe is from the Hubble constant. It tells us the ultimate fate of the universe. And it turns out it tells us the shape and weight of the universe. And that's because Einstein's gravity bends space. So imagine I have a heavy universe. The weight of the universe bends space onto itself and makes it finite. This is a universe, if I start here today and I head out this direction, given enough time, I will eventually come back to where I started. On the other hand, you can imagine a light universe. Well, space is naturally hyperbolic, as we would say in geometry. It's the shape of a saddle. It bends away from itself. In this universe, triangles, when you add up their angles, add up to less than 180 degrees. In the heavy universe, they add up to more than 180 degrees. And if that doesn't make sense, go out and try a globe and make a triangle, a big triangle on a globe, and add up its angles, and you will see that on a globe, the angles of a triangle add up to more than 180 degrees if you use string. And finally, we have the just right universe. The universe precariously balanced between the finite and the infinite. A universe which is just right also because the theorists who study the Big Bang, or right after the Big Bang, period which we call inflation, but that's a topic of another lecture, they think that the universe must be right on this precarious balance between the finite and the infinite for their theories to make sense. So, when I came to Australia at the end of 1994, I was moving to a new land and I decided I wanted to do something big. So measuring the age of the universe was one thing, but measuring its ultimate future seemed like the biggest thing I could think of. And so imagine the plan. You go through and you measure how fast the universe is expanding now, something I more or less did for my thesis, and then I look into the past and I recreate that experiment. I go and I look at these objects a long ways in the past, so I'm looking a far, far way away, and that allows me to see how the universe changes over time. If the universe isn't slowing down, well, then it's going to be coasting, and it will mean that the universe is infinite, it's empty, it's going to go on forever. On the other hand, if the universe has got a lot of stuff in it and it's heavy, well, there is a trajectory in which gravity wins, and faster than this, if the universe is slowing down faster than this line, well, gravity wins and the universe is heavy and finite. The other side of this line, gravity loses, the universe is light and infinite. And so to do this test, well, we need to be able to measure distances across the universe's past. And for that, the universe gave us something called a Type 1a supernova, an incredibly brilliant exploding star, which to understand, we need to first understand the life of a star. So the life of a star like the Sun is that our Sun was born 4.6 billion years ago, and in about 4 billion years it's going to puff up and eventually consume the Earth, crash down to a tiny little star called a white dwarf, a star about the size of the Earth but the mass of the Sun. Now if our Sun was instead born not as a single star but as a binary, that same process happens. But when a big star puffs up next to another one, this other star, the smaller star, will survive, and it can go through the same process. And that process allows this white dwarf to grow in mass as it siphons off material. And when it reaches 1.38 times the mass of the Sun, it becomes a giant thermonuclear detonation, producing light 5 billion times brighter than our sun, and synthesizing about 2/3 of the iron in the universe. These objects take about 20 days to reach their maximum brightness, and then they fade away into oblivion over time. So these objects, it turned out, were first looked at by Fritz Zwicky. Fritz Zwicky used a Schmidt telescope. Schmidt telescopes are not named after me or any of my relatives, but they're a special type of telescope that allow astronomers to take pictures of large portions of the night sky at a time. And so by taking photographic plates one night and then looking a month later, Fritz Zwicky and his colleagues could go through and find things that changed. And they discovered this class of objects, supernovae, which they named, that were appearing in the nighttime sky and seemed to be these powerful explosions. Now, over 30 years, they gathered a lot of data, and by 1968, they were able to make their version of Hubble's diagram, shown here by the one that Charlie Cowell did in 1968. And here, bright supernovae, faint supernovae are plotted against their redshift, low to high. And you can see the same thing that Hubble saw. The further away you go, the faster you're moving, or the more you have redshift, as we would describe it. And the scatter in this method was relatively large, about a factor of 30 or 40%, but it was consistent with the uncertainties in the experiment, which were very, very large. From this work, supernovae developed a reputation of being perfect standard candles, that is, almost all identical. And to test that, a group in Chile formed in the early 1990s, the Colón Tololo Supernova Search, and I met Mario Hamui, here just above my head, in France in 1990 when I was just starting my PhD, and they were just starting this supernova search. And so they told me about their plans to use these objects as standard candles. And when I visited Chile in 1991, the group was very depressed. They had been lied to. These supernovae were not all the same. 3 years later, when I was seeing Mario, he told me that actually there was a magic formula, a formula developed by his colleague and one of my colleagues also, Mark Phillips, which was that the supernovae, while not all the same, had a very specific pattern. And that pattern was that the ones that rise and fall quickly are fainter than the ones that rise and fall slowly. And we know from now that these things make and synthesize a little bit of iron. These do a lot of iron, and that process we can understand why this pattern happens in nature. So in 1994, when Mario came and showed me his diagram, and here's his version of the Hubble diagram, you can see it looks a little different than the other ones I've shown you because all of the dots, each supernova, lie exactly on the line. And that indicates that these supernovae were giving distances accurate to 6%. And that is really good by astronomical standards even today. From this work, this group eventually found 29 supernovae, and these have provided the fundamental basis of using type 1a supernovae as distance indicators. So in 1994, there were two breakthroughs. There was the one I've just shown you about how to use these supernovae, but a group at Berkeley had been working since 1988 to discover distant supernovae in the hope that they could be used to measure precision distances, had a major breakthrough. They went through and were able to define in a period of 3 months 7 such objects. And the thing that really contributed to that was a lot of hard work, but also the idea of technology enabling in the form of computers and large CCD cameras, which I'll talk about in a second. So that started a race between a group that worked on the supernovae, which was a group that myself and Nick Sunsef formed in 1994, who was competing with Saul Perlmutter's group. We did talk about working together, but the reality is we had very different ways of approaching the project at this time, and so it became clear that we needed to do the projects in our own ways, and this set up a competition between two teams, the High Z team and the Supernova Cosmology Project. And here you can see Saul Perlmutter, the leader of the Supernova Cosmology Project, and myself trying to punch each other out. We had a spirited competition, but I think most of the time we were very well behaved. And certainly one thing is clear, science benefited from the competition. Now, I told you in 1994 we had these two breakthroughs, and the one breakthrough that's implicit was technology. In 1994, the Keck telescopes came online. These were the new 10-meter sized telescopes, bigger than the 4 and 5 meter sized telescopes we had before. These were necessary to go through and take the redshifts and spectra of the supernovae that we needed for this experiment. The other thing that came along were these large format CCD cameras. These CCD cameras, you know, in your digital cameras and video cameras, but they came through the military, through astronomy, and were dispersed into civilian life by astronomers more than anyone. And in 1994, we had the first 4 million pixel detectors, or 2K by 2K detectors as we call them. And these things are about 100 times more sensitive than the ones, for example, in your iPhone. And although 4 million pixels doesn't sound very big compared to your iPhone, which typically has an 8 megapixel camera now, you have to realize in 1994 we were dealing with computers that were Pentium 2, 150 megahertz, and we were dealing with 1 gigabyte hard drives. And so we were usually taking 20 gigabytes worth of data a night, and so the technological challenge of sifting through this data and finding the supernovae was very hard. Now, just to make you think that we here at the ANU are not sitting still in technology, the ANU, through the Australian government, for Australia, has invested in the next generation of telescopes. And these are called, this new telescope that we've invested in is called the Giant Magellan Telescope. A telescope that is made up of 7 8.36 meter mirrors. And you can see these mirrors all work together to give us both a deeper and sharper view of the distant universe. The scale of this is represented by the semi-trailer at the bottom. Can you see this huge telescope has to be aligned to an incredibly precise accuracy of better than a micron or a millionth of a meter, and it's a very technologically challenging project that we expect to reach fruition over the next decade. It is a project we are doing in concert with the Carnegie Institution, the country of Korea, Harvard, Smithsonian, Texas A&M, University of Texas, and the University of Chicago, and the University of Arizona. So it's a great project for the future. And to show you that it's really happening, I was at the University of Arizona, where I was an undergraduate, which is making the mirrors. And here is the first mirror, 8.36 meters, polished to 19 nanometers. So a nanometer, a billionth of a meter across the whole surface. And that's mirror 1. It's done. Mirror 2, well, it came out of the oven, and here it is sitting there. And mirror 3 goes in to be melted in the oven early next year. And so this project is really coming online. So technology is the secret enabler to astronomy. And so I think astronomy with investments like this has a great future in the future here in Australia. So the technology of 1994, as I said, was very challenging to go through and sift through data like this to find the exploding stars. There's 5,000 galaxies in this image, and the key is to find the needle in the haystack, the exploding star. And that exploding star is this little smudge right here. And the way we find this is not by taking one image, but by taking two and separating them in time. So for example, if we take an image and we compare it to an image taken, in this case, 24 days earlier, we can see that nothing has become something here. This something, a supernova 5 billion years in the universe's past. A supernova which exploded before the Earth was formed. That is the power of cosmology, being able to look in the past. Fortunately, we can't look into the future. We can only speculate about the future. To give you an idea about how one of these trips works, I'm going to take you to Chile, to the CTIO 4-meter telescope, where we are getting ready for a night's observing. Here we see Greg Aldering from the Supernova Cosmology Project, silhouetted against the background because he's the bad guy. Nick Sunsef here is leading the observations. Nick is an incredibly finicky astronomer who wants everything to be perfect. And well so, because we only get 6 nights a year, because we have to share this telescope, of course, with all the other astronomers in the world. Nick makes sure that every image is precisely pointed and is of perfect quality so that my software can run on it, and then a team of people can go through and look for the candidates my software puts up and see if we are finding things that we can use for measuring distances. My software is okay, it's not perfect, there's a lot of junk. And time is of the essence because we have to go and look at these things across the globe at the Keck telescopes 36 hours later. So we have to process all that data as fast as we can so we can get onto with these large telescopes. Here we have Alex Filippenko and Adam Rees making sure that they get spectra. And of course there we're sharing the telescope time also with the Supernova Cosmology Project. Saul Perlmutter there. And they are too, of course, using the same facility. We were both using the same facilities, the best facilities that were on offer to do this work. So in 1997, Adam Rees contacted me. He was reducing and analyzing the data that we were taking for our next paper. And he said, well, what do you think of this? And what I saw was the following. Each supernova here is a point, and it has an error bar because the supernovae have an uncertainty. And these error bars are essentially tell you where 68.3% of the time the correct answer lies. So 1 in 3 chances it's out of here, but 2 out of 3 it lies within that error bar. And when I looked at these nearby objects, these are the objects of the Calan Tololo survey, the Chilean group, who are actually part of our team as well. And you can see that compared to this trajectory, on average, you can't tell what's going on. That's why we had to look a long ways away. These objects, the distant objects though, not a single one of them is consistent with the universe which is finite. But on average, you can also see that they don't lie in the yellow part of the diagram, the part of the diagram where the universe is slowing down. Instead, they seem to lie up in the top part of the diagram, the part of the diagram which says the universe is being accelerated by something unknown. In this case, the question then was, what's going on? People ask, did you say Eureka? And the answer is no. I think we really thought, geez, what have we done possibly wrong? So here we have Adam Rees's lab notebook where he first wrote down what this meant to him. And what he found when he did the calculations by the traditional method is the universe had negative mass, or effectively gravity was pushing rather than pulling. So I'm afraid there was no Eureka. There was a great deal of hard work to figure out what was going possibly wrong. After the end of that period, we decided nothing seemed to be going wrong. It was a crazy result. But as scientists, we ultimately have to report what we see, not what we like. And so in 1998, we put a paper out, and it turns out that the Supernova Cosmology Project was getting the exact same crazy result at the same time. And so it wasn't one, it was 2 papers that came out pointing towards an acceleration of the universe. And so these 2 papers are what eventually led to the discovery of the accelerating universe and to what became the Nobel Prize of 2011. And because this work is really done not by 3 individuals who won the Nobel Prize, but by 2 teams, I think it's very important to point out the teams. Here's the Supernova Cosmology Project and our own high redshift supernova team, dressed as we like to normally dress in white bow ties and tails, here for the first time ever together at the Nobel Prize ceremony in Stockholm. So that sort of gives you an insight of team dynamics. This team had never all been together in one place until the Nobel Prize ceremony. We all knew each other, we had all worked with each other, but because we were dispersed across 5 continents, we were never able all to be in the one place at the one time. We had a great time in Stockholm, and to give you a sense of what Stockholm's like, when you cut off the plane, if you're a Nobel Prize winner, first thing is they don't have you go through security in the normal way. Instead, they give you a driver and they whisk you off the airplane. And in my case, I came up and my driver said, "Hello, my name is Stig." And I said, "Stig? And I thought, I think he's going to get us around the streets of Stockholm just fine, thank you. The other thing you get to do is you get to meet the king. So here the king is presenting me the award, and the Swedes really wanted to know more than anything, not what came before the Big Bang, what is the universe expanding into? Nope. They wanted to know, what did the king say to you? So in my case, the king said, congratulations on behalf of the Swedish Academy for the Nobel Prize in Physics, and thank you very much for the bottle of wine, because I'm a winemaker, among other things, and I had presented him a bottle of wine before the ceremony, so I hope he liked it. And the final thing that they give you, in my case at least, was a princess. And here I am escorting Princess Victoria at the banquet, and when I look at this photograph, when I first saw it, I said to my wife, I said, geez, I look so glamorous with the princess on my arm. And that's turns out she didn't appreciate that as much as I had hoped. Turns out she also had the Swedish Prime Minister, a tall, handsome guy, so she didn't completely miss that. All right, so what is pushing on the universe? Well, we only have to look to Einstein for the answer. His cosmological constant, the energy that is part of space itself, well, that turns out can actually provide us a way to make gravity push rather than pull. This stuff, if it exists, makes gravity push as the fundamental way that gravity works in his theory, rather than pull. So by adding some of this stuff to space, we can go through and get the universe to speed up. Now, we're not sure that Einstein's version of this is correct. And so we give it another name, and that name is dark energy. Now, whenever astronomers use the word dark, it's because we can't see it, and that means, since astronomers look at things, we don't understand it very well. So dark energy is really stuff we don't understand very well, energy. So if you do a detailed analysis of our work, you come to the conclusion that the universe is a 30% mixture of normal stuff pulling on the universe and 70% pushing on the universe. So we really need a little bit of pull, a fair bit of push to make our observations make sense. Now, when we released these in 1998, the community was justifiably skeptical. I was skeptical. I couldn't believe the universe could be so crazy, but I knew that our measurements were fundamentally correct, that the supernovae were too faint to make sense, except for something crazy were going on. So a series of experiments were made, and the first one was done, or one of the first ones was done here in Australia, where a group using the Anglo-Australian telescope, an Anglo-Australian group, made a map of the nearby universe out to about 1 billion light years, making a map of 221,000 galaxies. And you can see that the galaxies aren't smoothly distributed. They sort of show this cosmic foam. And that foam is caused as a signature of gravity. And so it turns out, by looking at this foam and how galaxies are moving and the nature of this foam, they were able to very precisely measure the weight of the universe in gravity as it attracts. So they actually essentially to weigh attractive gravity here. And so the amount of gravity pulling on the universe by their measurement was 27% of the amount of stuff necessary to make the universe flat. So astronomers weigh the universe typically relative to the amount of stuff necessary to make the universe just right, to bring it to that precarious position between finite and infinite. The amount of stuff in the universe was 27% of the way there, at least the stuff that makes gravity pull. The other experiment that came, sorry, but the other thing I need to mention is that this, while not enough to make the universe flat, was still 5 times stronger than the gravity we could account for by the number of atoms that were in the universe. And so this stuff, of course, the shortfall, is what we call dark matter, or in the vernacular before, I don't really understand matter. This is stuff which we're hopefully going to get an insight into over the next couple years, but we think it's some undiscovered particle that, like a neutrino, can pass right through the Earth. So it has gravity just like atoms, but is essentially invisible. That's at least our hope what this stuff might be. So the other experiment that was able to be done was using the cosmic microwave background, this image of the universe taken right after the Big Bang, 380,000 years after the Big Bang. So these sound waves splashing around the universe have physics which is very similar to what we can do here on Earth very accurately. And so the physics tells us exactly how long these sound waves are. So, for example, one of these sound waves right here is about 450,000 light years long. And if you remember, how big something appears depends on how far away it is. But it turns out it also depends on the shape of the universe. If you look at things in a curved space, the light waves get bent. And so, not dissimilar to a car, objects, for example, in curved space that's finite appear larger than in a flat universe. So we can use that to make a precise measurement of the geometry of space. And when you do this, you find that those little bumps add up to being exactly what you expect for a universe which is geometrically flat. That is, has 100% of all the stuff necessary to be flat. Now, the geometry of space doesn't care if it's made up of stuff that makes gravity pull or push. It's sensitive to everything, and that allows us to do a little bit of subtraction. So, if we add up everything, we have 100%. We subtract off the stuff which is attracting, 27%, and that leaves us with 73% mystery matter. The same mysterious stuff that the supernovae found is pushing the universe apart. So what does that leave us? Well, it really leaves us with a mess. A universe where 4.5% of the universe are atoms, the stuff we know and love and are made out of. We represent a very small minority of what's in the universe. The rest of the stuff is dark matter and dark energy. Dark matter pulling, dark energy pushing. Dark matter pulls along with the atoms in almost exactly the same way. Now you might think, well, if we only understand 4% of the universe and we have to make up 95.5% of the universe, we just don't know what we're doing. And that may be a good call. But this model of the universe has been asked to predict many, many things. And over the last 13 years, everything it has been able to predict, we've been able to go out and measure and show to be true. And that is how science works. Reality is what the theory predicts. You know, when a theory predicts something to be true, that is the reality of the day. Now, it may be that there's something wrong with this model, and we're getting lucky at being able to predict things, but the things we predict are sufficiently complicated now that I think most people think that this model has essentially the truth embodied in it. And while it's probably not a perfect model of the universe, it is a model like Newton's gravity, which works very, very well at describing the universe we live in. Crazy, yes. Messy, yes. But it seems to be the way the universe is constructed. So, dark matter. As the universe expands, the amount of matter and atoms stays the same. So dark matter's density and gravitational effect gets smaller as the universe expands. On the other hand, dark energy is tied to space itself. As the universe expands, the dark energy gets created with the created space, and so it becomes stronger relative to dark matter over time. So this sets up a battle for domination of the universe. Dark energy versus dark matter. After the Big Bang, the universe was expanding. Dark matter would have been very dense and very strong. It would have been slowing the universe down. As the universe gets bigger and bigger, dark matter's domination is dropping. And at some point, about 5 or 6 billion years ago, it turns out the universe got sufficiently big before dark matter could slow it down that dark energy took over. And so the future of the universe, well, the future of the universe seems to be dark energy. The more space expands, the more dark energy can push against gravity, creating even more space and even more dark energy, leading to a runaway process. Eventually, the creation of space can happen even more quickly than light can travel. And so, galaxies we see today will literally be lost as their light goes through and is stranded in the expansion of space between us and those galaxies. In the oldest picture of the universe I showed you, taken with the Hubble Space Telescope, those galaxies that we see back 10 to 12 billion years ago, the light they emit today will never reach us. Those photons will be stranded in the creation of space between us. Now, just to allay some of your fears, attractive gravity has defeated dark energy in our part of the universe. You are not expanding, the Earth is not expanding, the Milky Way is not expanding. And that's because our part of the universe, dark matter and atoms, overwhelmed the expansion of the universe 13 billion years ago. And so our part of the universe quit expanding and collapsed. And there's a little sphere or ball of material where there was enough mass to do that. And that's what formed our own part of the universe. However, that part of the ball of the universe is gravitationally bound and will eventually merge into what we will call a supergalaxy. And so we believe the Andromeda Galaxy, which is one of the few galaxies in the sky that's coming towards us, will eventually merge with the Milky Way in 3 or 4 billion years in the future. And we're going to have this spectacular change in the nighttime sky from first 2 Milky Ways effectively in the sky, finally merging into a big ball of stars, into something that would look more like an elliptical galaxy, as we call them. But the rest of the universe, beyond that bound ball, will be accelerated out of sight. We will look out onto stars and nothing else. The rest of the universe will be empty. And that will leave cosmologists such as myself, who study the distant universe and galaxies, out of a job, because there'll be nothing left for us to look at. But the reality is, until we understand what is accelerating the cosmos, anything is possible. One of the most speculative ideas involves how dark energy might be a little different than Einstein's view. You know, when anything's possible, this dark energy can change over time and potentially even accelerate the cosmos at a faster rate than Einstein's version. And this leads to the potential, and I should say this is very speculative, of something called the Big Rip. If dark energy gets created more quickly than the creation of space, that is, if I have a box and I double the size of the box by the expanding universe, I get more than double the amount of dark energy, then that leads to a runaway that is able to penetrate to every part of the universe, including your own body and your atoms, and even down to breaking the universe down into essentially subatomic particles. And this point, as the universe expands more and more quickly, the density of this dark energy rises, and it eventually approaches infinity, allowing the dark energy to eat in to where the universe is already collapsed. And so this really has almost a human timescale to it. As the galaxies disappear, that happened a long time ago. Suddenly, the stars in the Milky Way will start disappearing. Eventually, the sun would disappear. And then sometime later, woof, every atom in your body taken far enough away that light cannot be transported between any of the atoms, and even the atoms themselves broken apart into quarks and electrons. So a very exciting end of the universe, and that leaves nothing. Well, it leaves something. It leaves an infinitely dense universe, which is expanding very quickly, and that has a certain synergy, I think, with Big Bang. So I kind of like it at some level, but it doesn't mean it's true. So this is one of the things we can go out and try to see if the universe is doing. At this point, there is no evidence, unfortunately, that this is going to happen. And I should say, as far as a theory of the universe, it has some real messiness associated with it, having this energy getting created more quickly with space. However, that aside, really, unless dark energy suddenly disappears, the universe will at an ever-increasing rate expand and fade away in front of our eyes so that people like me, 50 billion years in the future, have nothing less to do. Thank you very much.